Okay, let's say we go back to Galileo for a second. Galileo's head was on the block, right? Anybody? Anybody? Indigo girls? No? Wow, I'm showing my age. Dave's in the back room going, yeah, Indigo girls. Okay, what did Galileo do? Galileo went to the top of the Leaning Tower of Pisa and he dropped a massive cannonball and a very light cannonball. Okay. And he showed that those cannonballs hit the ground at the same time. And this was really confusing to people because from Aristotle's time, people thought heavier objects fall faster. Okay. And Galileo said, well, wait a minute, I'm not sure that's really true. Let me test it out. And so he did this experiment. And what he found was the time this one took to hit the ground was exactly the same as the light one. Okay. Why is that? Because they're both falling at g. There is certainly a bigger force on this heavier one, but it's also a bigger mass, and so its acceleration is g. On the lighter one, there's a smaller force, but it's a smaller mass, and so its acceleration is g, and so they both hit the ground at the same time. But now let's redo Galileo's experiment. And we're going to do two steps. Let's drop them sequentially. So we're not going to drop them at the same time. We're going to drop number 1. And we're going to measure T1. And then later on, we're going to do the second experiment. We're going to drop number 2. And we're going to measure T2. And now let me ask you a question. Is T1 equal to T2? And let's ask the people at home. And I'll set up your polling so you can answer. Is T1 equal to T2? A is yes. B is no. C is I'm too tired to answer. I'm still in my pajamas at home. Okay. Why don't you guys discuss it for a few seconds with your table and let's come up with an answer. Well, if they're yelling at me, they should put it in all caps, shouldn't they? Isn't that how you yell on text? See, the good news is they're paying attention, right? That's the good news, is they're like, hey, we can't hear you, which indicates maybe they want to hear me, that's all right. Okay, so no is the right answer. T1 is not equal to T2, even though it was in this case. This is still true. Nothing wrong with that. So what is going on here? How is it possible that T1 could not be equal to T2 here? Any thoughts? Turn on your mics. Turn on all your mics. And let's figure this one out.
They weren't dropped at the same time?
Okay. Possible that they weren't dropped at the same time. Yeah, that would certainly be true. If they were not dropped at the same time, then maybe there's some time differences. Okay, but pretend our clock is really good. Our stopwatch, we can say this one dropped there. Later on, this one dropped there. I measure those times. T1 is not equal to T2.
Is it like the same planet or whatever it is?
Okay, what is the planet that we're talking about? Well, let's talk about the one that we're...
Dropping onto the same, like,
Yeah. Let's say they're both dropping onto the Earth. Okay? I was asking my son the other day what he knew about the sun. And he goes, well, it's a big ball of gas and it's in outer space. And I go, that's great. You know what? Let me tell you a secret. You're on a planet that's floating around in outer space too. And he's like, what? What are you talking about? Yeah, same planet, Earth. Yes?
Are they dropped from the same height?
Drop from the same height. Good question. Yes, let's say they drop from the same height. What's your name?
What?
What's your name?
Megan?
Megan? Okay, good. So let's say they're exactly the same height. Yeah?
Are atmospheric conditions different?
Ah, okay. Let's make the caveat. There is no air in either of those cases. Okay. Which is kind of key in Galileo's experiment, right? Once you start including air drag, it becomes a lot more complicated. There's a great video on YouTube from David Scott, the astronaut. He went to the moon and he took a hammer and a feather and he dropped them and they hit the ground at the same time. Big old hammer and a feather, and they hit the moon at the same time. Why? Because there's no air on the moon. They both accelerate at the same rate, and if you get rid of all the air, it really does hit the ground at the same time, which is kind of weird.
Does the acceleration change?
Okay.
The times are different a little bit, but like a second.
Acceleration is basically the same, except you're getting close. Let's think about this right here. What force is acting on the ball? Gravity. But we just said no isolated force exists. I can't just draw one arrow in space and say that's our force. There must be something else. What?
I was stretching, but Earth is one.
I was stretching.
The math.
Yes.
It's done the gravity way.
That's our equal and opposite force. As the ball falls towards the Earth, it is pulling up on the Earth. Is this right? I mean, when I hold this pen up here and I drop it, am I saying that the Earth gets pulled up towards the pen? Yes, that is exactly what I'm saying. It doesn't get pulled up very much. Why? Because the Earth is pretty massive compared to the pen, right? So, why is the time no longer equal? It's because this one, we said, was big. This one is small. So what happens to the Earth in this case?
Moves up.
It moves further. That's exactly right. It moves up to there. So when the ball finally hits the Earth has moved up more than in this case. Because that ball was smaller. It pulled on it with less force. Okay, and this is kind of like weird to think about. And you might suspect that the difference in times is going to be very small. T1 is certainly less than T2, but it's not much less. And I wanted to figure out how you would do this experiment. So I did a calculation the other day. It turns out if you can measure a difference in time that is 1 femtosecond. Anybody know what a femto is? 10 to the minus 15. Okay, that's a femtosecond, which you can do, right? You can do that with atomic clocks. You can do that with lasers. So a femtosecond difference in times you could measure. How big an object would you have to drop and from how high? It turns out if you drop a tennis ball from the top of the Empire State Building and then you drop an oil tanker full of oil from the top of the Empire State Building and the whole thing's in vacuum, you will get a difference in time of about a femtosecond. So it's a slightly difficult experiment to do, but it really does sort of indicate that everything is pulling on everything else. In fact, the moon in its orbit, right? The Earth is pulling on the moon, but the moon is pulling on the Earth. Where do you see that? In the ocean, the tides. The only reason that we have tides is because of the moon. The moon going around pulls on the Earth, distorts the Earth, pulls on the oceans. Those oceans slosh back and forth depending on where the moon is. It's kind of a nice little symbiotic relationship we have between the Earth and the moon. Okay.